Hello everyone, welcome to engineering study, and today we are going to cover total effective and pore stress. And in my previous lectures I have already covered soil properties and soil classification, and today I am going to cover this chapter. This chapter is very important for the upcoming lessons like compaction, consolidation, shear strength, bearing capacity, okay, etc. And so learn this chapter, understood this chapter very carefully and write each and everything which I have written in this board. Okay. So first go through this term total effective and post stress. What is stress? Stress is a very important term in our engineering works. Okay. So what is stress? Stress is actually the inner resistance of a material. When you apply some load on this material, look into this pen, you can't deform or deflect this pen so easily. That means there is some amount of inner resistance created in this pen which is resisted the outer load. This inner resistance is stress. Okay. So this is stress. Stress is a inner property of a material. Okay. It is created in the inner side for the outer load. Okay. And now go through this total effective and post stress. Okay. So we already know that soil has three parts: solid, water, and air. And first know the unit of stress. Unit of stress is Newton per meter square. Newton load, Newton per meter square. Force by area. So total stress means stress due to the solid, stress due to the water, and stress due to air. But as the weight of the air is so negligible, that's why we can neglect the pressure or stress due to the air. So total stress means these two terms: pressure due to the solid and pressure due to water. Okay, this is total stress. And now effective stress. Effective stress means stress due to the solid part. That is called as effective stress. And then pore water pressure. Pore water pressure means stress due to this water. Okay. So these three terms: total, effective, and pore water pressure. Total means the stress due to the solid and water. Effective means stress due to the solid, and pore water means stress due to the water. These three terms is important. Okay. So now first go through this term total stress. Total stress means the total stress at any point in given plane section in a soil mass is due to the self weight of the soil above that section, and it can be calculated by total force by area. Look into this definition. Okay. As we have already covered unit weight, what is the unit of the unit weight? Newton per meter cube. Okay. And look into the unit of stress, Newton per meter square. Now, if we multiply it with into meter, then we will get the stress, Newton per meter square. So, what this length? Meter. This is actually height of the soil above concerned section. That means, look into this diagram. This is a point A, this is height H, and this the unit weight of this soil is gamma 1. So stress at point A will be gamma 1 into H. Now look into this definition. Total stress at any point A. Let us guess this point is A. In given plane section in soil mass is due to the self weight of the soil above that section. Self weight of the soil above this point A. That is total stress. So how you can calculate the total stress? The unit weight of this soil into height of the soil section. gamma 1 into H. Now if I tell you that calculate the total stress at point B, at this point, and height of the soil is H1. Okay, so this will be gamma 1 into H1. Gamma 1 into height of the soil above point B. So at this case, this soil will not be considered. Okay, so I think now this definition is clear to all of you. And now total stress is the combination of two stress, effective stress and pore water pressure. Now go to effective stress. Okay, these are the stress are being transferred by grain to grain contact, leading to decrease in the void ratio, increase in the shear strength, stability and bearing capacity. So when you apply some load on the soil grain, as the soil grains have voids, void means free space. When you apply some load on the soil grain will come closer to each other. Okay, and as it will come closer, the denseness will increase and void ratio will decrease. That means the space of the voids are decreasing as it come closer to each other. Okay. So due to coming closer to each other, this soil will increase its shear strength, stability and bearing capacity. Okay. And now go to this picture. These are the soil grains. These are the soil grains, and when I apply load, it comes closer to each other. And now what is stress? Stress is total load by connecting area. Total load by connecting area of contact. And now you can imagine that soil has millions of soil grains. Is it practically possible to find the actual contact area of the soil grain? It's clearly no. Okay, so we can't calculate the effective stress directly. We have to calculate it in a reverse way. How? That is, effective stress is equal to total stress minus pore water pressure. Total stress you can calculate unit weight into height of the section, and pore water pressure you can also calculate, that is gamma W, unit weight of water into height of the water table. Okay, that I am coming next. Okay, so that's why effective stress is being calculated by a reverse way, that is total stress minus pore water pressure. Okay, and now pore water pressure. It is a pressure caused by the pore fluid. It is equal to weight of the water per unit area of concerned section. Okay, and write down a note here, that is since since water pressure acts all around the soil solid and which is equal in magnitude, so it does not force the soil solid to come in contact with each other. That's why it is also called as a neutral pressure. Now look into this note, write down that note and look into this diagram. So what I have told you in this note, that this soil solid will be surrounded by the water molecule, by the water below water table. This soil grain is under water table, so this soil grain will be surrounded by the water, and the water will create same amount of force around the soil solid. Okay, that's why each force will be neglected with each other. That's why it is called as neutral pressure. That means it does not force the solid to change its shape, as in every direction it has same magnitude. Okay, so write the note. And now how we can get the pore water pressure? That is equal to height of the water table above constant section into unit weight of water. And all we know that unit weight of water is 9.81 kilonewton per meter cube. Okay. And next, also write a note here. Height of water above constant section is either calculated by observing water table above that section or by watching the height of the water in piezometer, Pizeometer, which is inserted at that section. And after that note, draw this diagram. Here is water table and is inserted, and I have told you to get the pore water pressure at this point. So actually it is quite impossible to get the exact height of the water table and below ground level. So what we generally do, we insert a piezometer, a tube like this, and when we insert this tube, as the water, this is whole soil, as the water below this soil is under pressure, and when it gets some free space, it will rise in this tube. And how the amount of rise will be the amount of pressure inserted the water in this soil. Okay, so after getting this height, you can understand that how amount of pressure generated by the water inside this soil. Okay, so then you can multiply this height into unit weight to get the pore water pressure. Okay. Now we will take an example, that is in submerged case. That means water table present at this point, and here is soil. This is soil, and the full amount of this is covered by water. Okay. Now this height is h, and this one is h1, a, b and c. Okay, so when the soil is under water table, what we have known, that the unit weight of the soil is gamma saturated, and unit weight of this water is gamma W. Okay. Now for point A, write it down for point A. Okay. For point A, total stress, pore water pressure U, and what will be the effective stress. As there is no soil above point A, so that's why total stress will be 0, no water, 0 and effective stress will be 0 at point A. Okay, and now draw a diagram beside this. Okay, at point A, this is a total stress diagram. Okay. And this is a point B. At point A, total stress is 0. This is a imaginary axis, and here 0, and from point A, total stress is 0. Okay, and at point B, at point B, okay. So total stress will be, there is only water. That means unit weight of water gamma W into H1. Gamma W into H1, kilonewton per meter cube into meter height. That means stress will be kilonewton per meter square. Okay. And at point B, pore water pressure equal to same gamma W into H1, as there is only water, and now effective stress will be gamma W into H1 minus gamma W into H1, that is 0. Why 0? Because there is no solid. Effective stress generated by the solid part of the soil. So as there is no solid, that's why effective stress at point B equals to 0. But total stress gamma W H1. Okay, now look into this. Guess H1 equals to 3 meter. Okay, and so it will come like this. H1, guess H1 equals to 3 meter, so 3 into gamma W. Here, guess H1 equals to 2 meter at this point. So at this point, it will be 2 into gamma W. So it will increase like this in a triangular manner. Okay. And now at point C, what will happen at point C? At point C, total stress equals to gamma W into H1 plus unit weight of the soil gamma saturated into H. Okay, and what is the pore water pressure? The water table present at here. So the total height of the water table from this point is gamma W into H plus H1. Height of the water table from the constant point. Okay. Then multiply it with gamma W. Then you will get the pore water pressure. So gamma W into H plus H1. So effective stress will be this minus this. That will be gamma submerged into H. Now at point C, look here, the total stress diagram, gamma W into H1 plus gamma sat into H. That means if there is only water, the graph will come like this. The slope will not change, but as there is soil, the total stress will increase from above ratio. And how it will increase? Like this. Okay. If there is only water, then it will be gamma W into H plus H1, this value. As the soil has came, the total stress amount will be increased from here. So like this. The graph will be like this. Okay. So now draw this diagram like this. And now this is the diagram of total stress. Now look into the diagram of pore water pressure. Here it will be like this. Okay. The slope will not change at this point. Here gamma W into H1 and here gamma W into H1 plus H. It will come in a triangular manner. Okay. This is a diagram of pore water pressure. And now draw the diagram of effective stress. Look, effective stress at point A is 0, point B is 0. Here 0, point B is also 0, but point C, that is gamma submerged into H. It will come like this. This is a diagram of effective stress. Okay. Now, due to the surcharge load, here is a soil and the water table present bottom of the soil. Here is the water table. Okay. And here is the water and this is the soil. Okay. But the difference is here is a surcharge load. Surcharge load, and the unit of this load will be given as Newton per meter square. That means you don't have to multiply anything with this surcharge load, as it is already covered into a stress, Newton per meter square. So it is a constant Q Newton per meter square. So first, this is a point and B point and C point. Okay. For point A, total stress will be Q here, as there is a surcharge load. Okay. Any height will not be multiplied with Q. Okay. As it is in already Newton per meter square, the unit of stress is already there. Okay. And pore water pressure will be 0, effective stress will be Q minus 0 will be as Q. Okay. So now draw the diagram. Total stress diagram. And now consider for point B. For point B here. So Q equals to total stress equals to point B. Surcharge load is constant Q plus unit weight of this soil. Let us consider that is gamma into height of the soil H1 into H1. Okay. This will not be saturated as it is above water table. Okay, gamma. Okay. And pore water pressure will be 0 here. There is no water. And effective stress will be Q plus gamma into H1. Okay. Now points, and for point C, total stress will be Q plus gamma into H1 plus, and the soil below water table will be gamma saturated into H. Okay. And pore water pressure will be gamma W into H. Okay. And effective stress will be this minus this, Q plus gamma into H1 plus gamma submerged into H, as gamma sat minus gamma W is gamma submerged. Okay. Now draw the diagram. Here look into this term. Here total stress Q. Here total stress Q plus gamma into H1. Here total stress Q plus this. That means Q is constant in every point. Okay. So now we can draw this like this, like as Q is constant and this is Q, a rectangle. This is Q. Okay. But here Q plus 0, that means here it is 0, and Q plus H1, again a triangular manner will come like this, and then gamma into H1 plus gamma sat into H, and then again it will increase and a triangular manner will come. This is Q and this is gamma W into gamma into H1, and this whole is gamma into H1 plus gamma sat into H. Okay. Now if we draw the pore water pressure, here point A 0, point B 0, and point C gamma into H1. Here is 0, here is 0, here is 0, and then it will come in a triangular manner. Pore water pressure. Okay, and then effective stress, look, here is Q, Q, Q. As Q is constant, you can draw it in a triangular manner. Okay, and then look into this diagram very carefully. It will come like this. Okay, from 0 to gamma into H1. It has come like this. Okay, but here gamma submerged into H1. Okay, as gamma submerged, as so the value, there is a two chance. One, it will go like this, and another it will come closer. Slope will be different, but come closer. Okay, so what it will be? As the value of gamma submerged is less than gamma saturated, so it will come closer than the previous part. Here the graph has gone like this, and here it will come closer from the previous part, and like this. Okay, so this is gamma H1 plus gamma submerged into H. Okay, and now this is a home task for you all. And here look into this. There is some amount of capillarity in the soil. This is a water table, and the whole is soil. Soil is present here on the whole section, and for this water table there is some amount of capillarity happening in the above soil. So I am doing the first two things, that let us, this is point A, B and C. Okay, for point A, okay, look, the pressure or stress, generally we assume that when we apply load, the pressure or stress generally act in the downward term. Okay, act downward, but capillary force is acting on the upward section. So at point A, total stress will be 0 as there is no soil above it, but pore water pressure minus H1 into gamma W, minus H1 into gamma W, as the water giving the pressure from the downside. Okay, like this. So pore water pressure will be minus H1 into gamma W, and effective stress will be total stress minus U, so H1 into gamma W. This is point A, and for point B, total stress will be, as this soil is saturated due to the capillarity, so H1 into gamma saturated. Pore water pressure at this point is 0, as there is no water table above this. The soil is saturated due to the capillarity. Okay, this capillary water will not give pressure to the downward direction. Okay, so that's why the pore water pressure at point B is 0 and effective stress will be total stress minus U. You can get this, and so complete the rest part and draw the respective diagram of this. Okay, I am just give you a clue for the pore water pressure. Here minus, that means it will come in this direction. This is a respective axis and it will come like this, and this signifies the minus term, minus H1 into gamma W, and complete the rest, and I will discuss this whole thing, this home task in my next lecture. Okay, thank you.